The next section is on photometry. So photometry means measuring the brightness of an object, usually through a filter. So the brightness that is recorded on a detector comes from everything the light went through to get to you. So brightness, the intrinsic brightness of the source, plus the brightness that the background is contributing, that the source is projected onto, and any light losses that come with going through lenses or bouncing off mirrors or going through filters or literally entering the detector. So it's a combination of all of those things. Every astronomer does things a little bit differently. And when I was learning how to do photometry, it was kind of amazing to me that any two astronomers working on the same object in the same data ever get the same answer, but they do. That's because the choices one astronomer might make differently than another astronomer at an early step then get compensated for at a later step. Everyone is making choices that they think is right, but they'll all have to calibrate back to objects of known brightness. And in that fashion, you make sure that the answer you're getting is right, even if you're making different decisions along the way. The net shape of a point source is called the point spread function. Sometimes that's called the point response function, or PRF. Technically, a PRF is not the same as a PSF, but don't have to worry about that now. The PSF, what that means is, so a star at an infinite distance is truly an infinite point source. But by the time it gets through everything it needs to get to your detector, whether that's atmosphere or just simply the reflections off of the mirrors and going through the filters, all of that results in a distinctive pattern that is unique to the combination of detector and telescope and filter, right? So there's a unique pattern that is, the PSF is that unique pattern. And the PSF, even though the source is infinitely small, the PSF is surprisingly big. And you're going to have to worry about that in the context of photometry, because if you're measuring the total brightness from a source and you've got PSF extending over many, many pixels, you need to worry about what happened to that flux when you go to measure it. So you can measure fluxes from point sources like stars. If you want to measure extended sources from galaxies, things get a little different. So we're just going to focus on point sources like stars. So you have two approaches. You can use aperture photometry or PSF-fitting. So aperture photometry, we'll talk more about in a second. Basically, it just says, okay, count up all of the flux within a given aperture on the image. Or PSF-fitting, which says, okay, I know what the PSF is supposed to be. I'm going to match the source that I see to that idealized PSF. We'll talk more about both of these in a second. WISE catalog photometry is all PSF fitted, but some of the other columns that it gives you is aperture photometry. So aperture photometry should give you the same answer as PSF fitting when you're doing both right. So that if you think something's wrong with the PSF fitted photometry you get from WISE, it gives you the aperture photometry so that you can check and see that it's coming up with a reasonable answer. For Spitzer, in general, the IRAC photometry that you want to use is aperture photometry, and MIPS is PSF fitted. That's because the IRAC sources really only subtend 1 or 2 pixels in IRAC. And it's hard to do PSF fitted photometry when you're only really caring about a couple of pixels. And so aperture photometry works pretty well for IRAC. But for MIPS, the PSF extends over many pixels, and so it's easier and better to do PSF fitting for MIPS. Offhand, I don't know what every other data set you might encounter is doing, but you have to check the documentation in order to figure that out. So aperture photometry, that's going to measure all of the flux within an aperture centered on the star. Usually that's a circular aperture. And then you have to subtract off the flux from the background. So you put an annulus, like a donut, around the aperture to estimate the background and then subtract that off. This approach is quick, but can be fooled. It's not necessarily accurate. You can get large errors, especially if the background is complicated. And if you have a crowded field deep in the galactic plane near the galactic center, it's essentially impossible because there's just too many sources nearby. You do have to worry about fractional pixels. So think about that. If you're going to put a circular aperture on top of an image where the pixels are square, you've already got a problem. You already have to worry about fractional pixels. And that matters a lot in general, but particularly for Spitzer data because the units of the images are megajanskis per steradian. And so the size of the pixel in steradians matters. And then moreover, you need to apply an aperture correction. So usually for most sources, you're going to put the aperture pretty close to the center of the source, but then you're going to miss all of the flux that's outside that aperture. So you have to correct your aperture measurement to deal with the fact that you've excluded some of the flux. So here's an example. We've got the target object in the center. We've got an aperture set centered on that source. And then here we've picked a background annulus, which is close to the source, but specifically avoids this nearby source. So what you do is you sum up the pixel values in the target aperture. You worry about fractional pixels. Then you count up the total flux in the background annulus and worry about fractional pixels, and then scale that background to match the number of pixels you have in the aperture and subtract off that median background, and then you can convert the counts you're getting to brightness, which we'll talk about magnitudes in a little bit. So here's a more complicated one. Here we've got a source that's relatively bright on top of a highly variable background. So here we've got the target object, right? And that object is actually fairly complex. This is MIPS data. So you have the bright core, and then you have an airy ring around that bright source. So in this case, the object aperture is the red, and then the background annulus is right close to it. It goes from the green to the yellow. So it's deliberately selected to have the aperture as close as you can get to the star, because you're trying to take into account that there's highly variable background. And so you want to get a pretty good estimate of the background, but right close to the source. When you're worrying about PSF-fitting photometry, the important concept is that the response, the net response of the telescope and the detector and all the things your light went through before you detected it, is that response is always the same. It seems kind of weird, because when you look at an image, you've got bright sources, faint sources, everything. But it turns out that it's always the same. The physics is always the same. So the peaks of the bright sources are much brighter than the faint sources, but the shape is always the same. And when you have an image of a bright source, you can see lots and lots of structure in the PSF. So when you do PSF-fitted photometry, you take that known shape of the PSF and then match it to the point sources in the field. And when you scale it to match the peaks and all the other brightness that you're measuring, you're therefore taking into account the fluxes at great distances from the star, and you're getting rid of the complicated structure in the background or nearby sources that might be contributing to the flux you might measure if you were doing aperture photometry. So PSF-fitting photometry works best when you have a lot of pixels involved. When you have many pixels making up the PSF, then it works really well. So here's a MIPS PSF. When you look at it, when you just load it into your favorite FITS image viewer and you do sort of a standard scale, that's what you might think the MIPS PSF looks like. But it turns out it's actually much more complicated than that. This is a same source, but stretched differently. So you can see here, it's just got the point, the center, and the first airy ring. Turns out there's lots of airy rings. And on MIPS, the secondary is held in place by 6 struts. So you have 6 spikes, 6 diffraction spikes, because light is a wave. So all of that structure is embedded in the MIPS PSF. So you take the MIPS PSF, and then you scale it. You identify sources in your image, and you scale it to, you compare your fitted one to the known objects, and then you fit it to the objects you want to measure, and then you calculate what the brightness must be. So the main takeaway points for this section is that photometry is the quantitative measure of the brightness of an object. Conceptually, it seems really simple, but when you get into the guts of it, there's many, many, many buttons and dials and levers to try. And there's lots of different ways to do it, lots of different ways to do it right, but you have to make choices all along that make sense and keep testing along the way to make sure that you get the right answer. Pipelines, like most of the data that we're working with, should do all of that detailed choice making for us. Usually these pipelines are more reliable the larger it is, and therefore the more I trust it. So like big projects like GLIMPS or 2MASS or Gaia or PanSTARRS have these big pipelines that are tested to death. So you can be pretty certain that it's doing the right thing. And those big pipelines usually also have flags to tell you when the computer thinks something has gone belly up. Smaller projects, when they're doing photometry for just one region, that is where you might have more errors creep in because you have fewer people trying to bang against the pipeline and break it. But the trade-off is that those big pipelines like 2MASS, Gaia, Pan-STARRS have to work everywhere. So they have to work both in relatively isolated extragalactic fields and really crowded galactic fields with lots of background. And so the effect of that is that, for example, the Spitzer Enhanced Imaging products, the SEIP data collection, it doesn't go very faint because a decision was made that all the sources in that catalog should be real. So they have to be reliable. But the trade-off is that it's not very complete. It doesn't go very faint because that's the trade-off. GLIMPS is an entirely a galactic field project. So their pipeline is customized to deal with the issues of crowded fields and complicated backgrounds. And so they're able to go to much fainter sources much deeper than the SEIP data products.